Hello, my name is Gwendal Junot. I'm a PhD student at the University of Rennes. Today, I will present you joint work with my PhD advisors, Olivier Barret, Benoît Combal, and Gunther Musbacher. This paper is entitled SEALS, a framework for building self-adaptable virtual machines. Before talking about languages and virtual machines, let's talk about software. Nowadays, software evolve in complex and changing environments, such as cloud or embedded systems. In this context, they need dynamic adaptation to best deliver the service. For example, Netflix adapt the quality of the video they send you, depending on, among other, your bandwidth. On the other hand, we have software languages. Software languages can abstract concerns into high-level constraints. This has been done with memory management in language such as Java. The challenge we oversee is for language engineers to provide functionality for self-adaptation in their domain-specific language. In this paper, we present the SEALS framework. This framework helps language engineers to add self-adaptation in their languages. SEALS support the definition of, first, the language abstract syntax and operational semantics. Second, the correctness envelope defining the valid semantics for domain concepts. Third, the feedback loop and the associated trade-off reasoning. And finally, the adaptation and the predictive model of the impacts on the trade-off. But what are self-adaptable virtual machines? These virtual machines are a specific case of self-adaptable languages. If you want to know more about self-adaptable languages, our talk at Onward 2021 will present the concept. But it's the reification of a feedback loop, here a MAPK loop, in the operational semantics of the language. And in our case, we use a pluggable architecture for the adaptations and can delegate configuration responsibilities. We studied three motivating examples. First, mini-Java, an imperative general-purpose language, is configured by the language engineer to perform a trade-off between accuracy and execution time, depending on the CPU load. Roblong, an action language for robotics, is representative of imperative domain-specific languages configured by the language user to perform a trade-off between the execution time of an action and the energy consumed to perform this action. Finally, HTML is a declarative domain-specific language configured by the end user to perform a trade-off between the quality of the page rendering and the energy consumed to display it. However, the consumption being difficult to assess in this case, we use the transfer size as heuristics due to its proportionality with energy consumption. A self-adaptable virtual machine built with SEALS is composed of three parts. First, the framework in itself and its concept. Then, the modeling of domain with the implementation of the SEALS concept. And last, the adaptation process specified by the language. To better understand the concept involved, I will now present them using the HTML use case as an example, while following the workflow of a language engineer. The first step is to model the domain concept. As an example, we will take the block tag concept that represents an HTML element with an opening and closing tag. First, you need to create its abstract syntax. Here, it's HTML node block tag by implementing the node SEALS concept. Then, if the concept can be adapted, you need to create a correctness envelope. Here, the block tag interface that represents the part of the concept subject to an adaptation. and the method to change it correctly. After that, you have to define the semantics by implementing an operation. Here, it's the HTML operation block type. This operation should rely on the correctness envelope in its definition to be correctly adapted. From these operations, the framework will generate a concrete visitor containing adaptive semantics for the adaptive concept and normal semantics for the other. Additionally, you can define domain-specific adaptations. These adaptations, when activated, receive a correctness envelope instance on which they apply transformation to adapt the semantics relying on them. The second step is to specialize the adaptation process. First, you have to specialize the adaptation context that act at the common knowledge of the MemKey loop. This specialization includes defining the key performance indicator of the trade-off and the monitoring sources. Then, you have to specialize the feedback loop and implement the concrete monitor, analyze, plan, and execute steps of the MemKey loop, as well as the trigger of the loop, meaning if it's periodic or if it should be triggered when a particular concept is executed. And finally, you need to specialize the self-adaptable language class to connect all the components needed by the framework. We implemented a Java version of this framework, creating interfaces for the domain concept to implement and abstract classes to be specialized for the adaptation process. But let's look a bit more in detail on how the adaptations are performed using the correctness envelope. When the semantics of a node is called, it goes through the visitor pattern accept method. If an adaptation is activated, an instance of the correctness envelope is created and sent to the module when you call the adapt function. This instance is initialized to perform the default semantics if not changed. During the adapt method, the adaptation can perform all the action allowed by the type defined as correctness envelope. It can, for example, get properties value or change values using getters and setters. Finally, the modified instance of this correctness envelope is sent to the visitor with the node and execution context to perform its adapted semantics based on this transformed interface. To evaluate our approach, we first evaluated the relevance of the proposed constraints. A self-adaptable virtual machine has two mandatory components. First, the feedback loop, or in this case the MemKey loop, is abstracted into the adaptation context for the knowledge part and through the feedback loop concept for the monitor, analyze, plan, and execute steps. And second, we have the operational semantics, which is supported by the adaptation concept, the operation concept for its definition, and the correctness envelope for its adaptation capabilities. Additionally, we also abstract their interactions. Then we looked at the assurances provided by the correctness envelope. First, the system prevents adaptations execution as the default behavior. Second, to allow adaptations, the language engineer has to explicitly specify what can be adapted, the subject of adaptation, and how it can be adapted, the methods of the declared Java class. And finally, the semantics changes of a concept are bounded by the set of possible instances of the correctness interval. We also performed evaluation of code size and performances. In short, we reduce the size of the code, but when there's a lot of concept, like in MIGI Java, the implementation of the operation as classes are heavy in terms of line of codes and make the framework looks bigger than the uncrypted version. For performances, we do not see a general trend, but good results for HTML and Roblong call for future work. In conclusion, the SEALS framework provides abstractions to define the abstract syntax and the semantics of a language, as well as the feedback loop and associated trade-off reasoning. In addition, the frameworks also support the definition of adaptations and restoring them using correctness envelope. For future work, we envision better tooling to help the language users better visualize the adaptation capabilities of the language. A better management of the feature interaction between adaptations, a principled approach to self-adaptable virtual machines, and further work on performances of the framework. Thanks for your listening.